Well, good afternoon. I just wanted to do the last step in calibrating or performance testing my HP 435B. In the previous videos, we've looked at the power reference, got that to be 1 milliwatt. We've looked at zero carryover and confirmed that we're within spec as we move from range to range. We've then used the 11683A to check that our range accuracy is correct. So now the last step to do is to check the calibration factor here. So what I'm going to do that is we'll set ourselves to 1 milliwatt and 1 milliwatt on the range calibrator. Let's go to local here. I'm going to zero that out. Okay, we'll bring that up. And you can see that from where I did the work yesterday, we're still very close to 1 millivolt. Sorry, 1 millivolt, 1 volt full scale deflection. We're at 999.6 millivolts there. So I think that's probably a reasonable position to start with. And I have my application again that can help us go and capture the data that we need to do the test. So let's start with calibration factor. We're at 100. We're set. So let's go. All right. So there we go. We're set at 100. I forgot to point out, drink of the day is an afternoon, evening vodka soda made with soda from my soda stream. I probably should have said this up front. The reason that the calibration knob is here is to normalize the thermocouples across a frequency range. If you have a look at let me see if I can, we'll see if the camera catches that. But you can see that on this power sensor, there's a set of frequencies, and then there's a calibration factor that gets dialed in to normalize this sensor across that range of frequencies. On the more modern sensors, it's in a piece of non-volatile memory on the actual sensor itself and gets read directly off by the power meter. And it makes it quite good. How you would use it is, for example, if we were measuring a 1 gigahertz signal and we wanted to check the power on this, what I would do is I would go to my sensor, I would look down to where it said 1 gigahertz. In this particular case, it says 98% calibration factor. And so then I would dial in 98% on this knob here and take my measurement. For a more advanced meter like the 437B, you can actually program a set of the complete data for a sensor into the meter itself. So then all you need to do is select the sensor and then tell it what frequency you're measuring at. They didn't have that functionality in the 438A, I think. Not sure why they didn't do that. And then they, as I said, in the later sensors and meters, it's in non-volatile memory on the sensor itself. So you just plug it in, it syncs up, it reads in its calibration factor table, and then you just tell it what frequency you're measuring, and Bob's your uncle. Anyway, that's why the calibration factor exists on the meter. Okay, so let's take a look at our report now. Okay, so now we can see our report and we're within spec on all the calibration factors as well. So zero carryover was good, accuracy test was good, and the calibration factor test was good. Plus we adjusted the 1 milliwatt reference into spec with the 432 and the 478A thermistor mount. So overall, I think we're good to go. I think we can declare this unit to be successfully working. So now that I've done that, I will run this guy through the same process, just because I have it up here on the bench right now. And then we'll take a look at some of the dumpster dived gear, or dumpster dove? Anyway, some of the dumpster required gear that I have. I have a couple of items. We'll take a look at those, and we'll see you in a future video. Hope you found this interesting. Catch you later.